These were the notes from last time, right?
Yes, yes. So we're just going to continue a little bit from there, or a lot from there, and then at some point I'll switch back to the presentation. Okay.
Which will be uploaded
Eventually. At some point.
Okay, yeah, I think I see how the stream relates to magnetic
Give him a
field.
second, come on.
Gather myself together.
Remember that was like last time I was really
All right,
confused.
good. So let's go to this and let's quickly remember what we had in the previous lesson, which we didn't finish, and I'm going to finish now before switching to the second part. So we were talking semi-quantitatively about elasticity and geometric nonlinearity, meaning the fact that when moment you have a sheet, just using the fact that you have a sheet and you have geometry, meaning things can move around, this creates important nonlinear effects, which are very relevant to almost any experimental platform that involves 2D materials. Now, let me briefly remind you what it was that we saw in terms of how you define continuum elasticity. Again, once you almost have no lattice left, we define what we call the strain tensor, right, which is just the difference in the deformation. So every atom moves a little bit, and we're interested in the differences between neighboring atoms. That gives me the strain. And then there's Hooke's law. Hooke's law connects forces, or the stress tensor, to the strain, or the deviations, the deformation. And it's connected by some kind of horrible fourth order tensor. But essentially this is just Hooke's law because F equals K times X. Right? Everything else is just indices. The second thing that I pointed out to you, and I want to stress that there's no way that in one class, I'm going to be able to teach you the tricks and trades of how you solve problems in elasticity. But I do want you to take from this type of class what the formalism is and how it helps us think about problems. So one of the things that's very important or very useful when doing theoretical work on two-dimensional materials is the fact that you can always map them to electrostatics. The way it's done in elasticity is by something called the area stress potential, which is defined as just a function, a scalar function, chi, equivalent to the electrostatic potential phi. And the components of the stress tensor, sigma xx, sigma xy, and sigma yy, are given as derivatives, in this case second derivatives. Okay, why second derivatives? It has to do with the fact that with elasticity, you always get fourth order equations instead of second order equations like you get in electromagnetism. And this has to do with the fact that you have bending. But we're not going to go into that here. The point is that you can show that if you define the stress tensor in terms of these relations, so sigma xx, there's an error here. Sigma xx is the second derivative in y of x, and sigma yy is the second derivative in x of chi, and sigma xy is the mixed derivative. Then it obeys Hooke's law in the sense that should be here somewhere. Here, yes. Hooke's law tells us that if there isn't any external forces, sigma equals kx, so then the divergence of the stress tensor must equal 0. This is the same as saying that we're in equilibrium. The forces inside the material are in equilibrium. There's no as I move through the material, the forces don't change, and that means that I'm in equilibrium. You can show that defining this potential is equivalent to requiring this, meaning every function chi is going to create a stress tensor that obeys the equilibrium. And this is similar to how when we have Gauss's law in electrostatics, right? If we define the electrostatic potential, then by definition, taking the electric field to be the gradient gives us Gauss's law. Okay, so what that means is that you take the potential and the requirement of equilibrium is equivalent to requiring that the fourth order equation on chi equals 0. So any function which is a solution of the bi-Laplacian describes stresses in an elastic material that are in equilibrium. Now, presumably there are many such functions, that's true, and as usual what will be important is boundary conditions. So in a way this is telling you that the boundaries of your system are always going to be important, and we'll get back to that in a moment. The second thing we did last week was to both simplify and complicate. We simplified by saying, forget about this horrible fourth order tensor. Let's take the simplest continuum limit of an isotropic system where there's no lattice left, and then there are basically two elastic constants. They're called the Lamé coefficients. It's completely unimportant what they are, because people keep on defining more and more elastic coefficients that are functions of these Lamé coefficients. Okay? But the most important thing that occurs when we allow a system to bend is that we're effectively changing distances. So if we have distances in the plane, now we have distances out of the plane. This is like changing the metric of the system. It changes the relation between two different points in the plane. Their distance is no longer x, it's x squared plus z squared square root. And what this means is that the strain tensor gets this z squared behavior. This is just the Pythagoras equation, the Pythagorean theorem written in terms of derivatives. Okay, why is it important? Because it's nonlinear. So you didn't do anything except allow your system to bend. Okay, you take a graphene sheet and you do something like this, or you just suspend it in the air, and you automatically get a nonlinear behavior. It doesn't matter what you do, your behavior will be nonlinear. In terms of the relevant equation, what happens? You get a source term. Okay? The right-hand side is no longer 0. 0 is only when it's flat. Instead, you have y, which is again an elastic coefficient. It's equal to E times the thickness divided by 1 minus the Poisson ratio squared, or some set of functions of these two guys. That's in the notes if you're interested. But R is the determinant of the curvature coefficient. So basically you take every area on your material and you calculate the curvature, the principle of the second derivatives, the product of the second derivatives at every point. Okay? The product of these second derivatives is how much my material is curved at every point. And this, so you see this is just the determinant of the second derivative matrix. And this acts like electrostatic charge. Okay? So what that tells you is you cannot have curvature without stresses. I cannot take a system and curve it without creating stresses in my system. Because I might not be able to see it, but curving my material pushes the atoms away from where they would like to be. And what this tells us, for example, is that one of the ways that a material will respond is by trying to relieve these stresses. So this as just a quick example, does anybody know the pizza theorem? Pizza triangle theorem. You ever heard of this? Why do we always hold the pizza? Why is it that the pizza, if you hold it flat, it always flops over? But if you curve it like this, right? If you make a triangle, then you can eat it. The answer is this. So the product, the total curvature, is the product of the two principal curvatures. What that means is if I have a cylinder, something like this, which is flat in one dimension and curved in the other, the product is 0. Because it's 0 times something which is non-zero. Okay? So if I allow my pizza to be flat, it can deform with 0 energy, because one dimension remains flat and the other dimension becomes curved, and then my pizza flops. But if I force it like this, then I've created curvature in one direction, and now if it flops, it will have curvature in 2 dimensions, then the product will be non-zero. This will create stresses in the system, and that costs energy. Okay? So that's why modern elasticity theory can tell you how to hold your pizza. But notice, it's really the same thing, right? I took a pizza. It happens to be a thin sheet, right? Where bending costs much less energy than stretching, right? Stretching a pizza is not so easy. Bending it is very easy. And this is what it tells you. Okay. So what I want to do now, I go back to the notes from the previous class. And I want to do 2 canonical examples. Again, I will quickly go through how you do the math. The purpose is not that you should remember how the math is done, because you can always look up the notes. The purpose is to show you both how the formalism of continuum elasticity allows us to solve complicated problems, and also to teach us the guiding principles. Okay? So the first canonical example I want to teach you is a very simple one and also extremely experimentally relevant. What happens if I take a sphere, okay, And I take a sheet, and I put the sheet, I drape it on part of the sphere. So I create a spherical cap. Okay, all I do is I take my sheet and I force it onto the sphere. I make it very big so that I don't have to worry about boundary conditions. I cut my big sphere down at the cap, okay? And I leave just the spherical cap, and I want to see what happens to my material. And as I will show you, by definition, the only way that you can do this is if you create strain and stresses. So your entire sheet will be stressed. Okay? So how do we do this mathematically? The first thing we're going to do is we're going to do a small angle approximation. Meaning we're going to take a parabolic approximation. So z is going to be r naught square root of 1 minus r squared over 2 r naught squared. That's just the usual shape on a sphere, right? I start from here, z is like this, and I go down as a function of r. I'm working in 2 dimensions with radial coordinates. And so we're going to assume that this is more or less r naught minus r squared over 2 r naught squared. Over 2 r naught.
Should it be 4?
Hmm?
Yeah.
Yeah, I think inside it should be
No, here
without
there
the
shouldn't be,
two.
here there just shouldn't be 1 over 2.
Yes.
That should be like that. And then I'm just going to rename things. Again, just to save some algebra, we're going to call this z naught minus 1 over 2 alpha r squared. Okay? So the idea is that alpha is a small parameter. I mean, a small angle approximation. I take my spherical cap. I'm assuming it's a very small part of my overall sphere so that I have very, very small angles. So alpha is a small parameter. Z naught is just some number, which tells me how high I am above 0 elevation. And this is my arm. Okay, and now the truth is that it's much easier to solve this problem directly with the strains. But we're going to do it with this area potential so that we can see how the physics of the area potential show up. And the second thing is we're going to use axial symmetry. So the functions are a function of r. I only wrote to you all these horrible tensors in Euclidean coordinates. So please trust me when I write down the same results in spherical, in polar coordinates. Okay, you have to take the tensors, open Dale in cylindrical and polar coordinates from Wikipedia, and copy out the various terms. You've probably opened this Wikipedia page, and then all you look at is the Dale squared. Yeah. But there's so many others. All those so many other things, they come from elasticity, where you have to do these tensors. Okay.
I have to check the curl.
So I remind you that the equation of motion is the fourth derivative of chi is equal to minus y, which is just some coefficient, times the Gaussian curvature. Okay. So in polar coordinate, this is 1 over r, d by dr, r, d by dr. This is the Laplacian, right? Square. Okay, so some horrible fourth order equation is equal to minus y 1 over 2r, d by dr, dz by dr squared. And notice that dz by dr is not part of the solution. It's, right, I've forced my material into a given profile. I know what this is. I just need to calculate the first derivative and square it, take another derivative and divide by r. It's easy to see that this will give a constant. And that's why, of course, we do the small angle approximation, because a parabolic approximation by definition has constant second derivatives, which gives us a constant curvature. So the answer is just minus y alpha squared. That's why I defined alpha. Okay? What does this mean? I have a fourth order equation, and this equation has a source. Fourth order equation, how many homogeneous solutions do I have? 4, right? So here are the 4 solutions. Chi is equal to some constant plus b r squared plus c log r. Log r, I remind you, is the homogeneous singular solution of the Laplacian, right? That's the one where you take the Laplacian and you get the delta function. So take Laplacian squared, you get horrible delta function. Sorry. Plus d r squared log r. That's the one that's a delta function when you take a fourth order Laplacian. So if you want, this is the source of singularities in the second order Laplacian. Okay, this is a type of singular charge, and this is a different type of singular charge. These are disclinations and these are dislocations or something like that. And then I have my inhomogeneous term, which is just minus y alpha squared over 64 r to the fourth power. Okay? And now I need to apply boundary conditions. This is why I did it, so that we can see how the boundary conditions work out. So this one I picked to be 0. Why do I pick this one to be 0? This will be our first boundary condition. Yes, sorry. My apologies. So we kill the constant. This will be our first boundary condition. Chi is a potential. It all things only depend on its derivatives. I can choose it up to a constant, right? Potential. Gauge freedom field. Can you guys guess what the other boundary conditions will kill? What do you think is C? C is 0. Why is C 0? Because if I take second derivatives, I get the singularity. This is the singularities of the force. So if I have spots where I press on my material, yeah, that will create delta function forces. That will give me a non-zero part. But here in my thing, everything is flat, everything is smooth, so there are no singularities. Yeah, you can of course also show this mathematically. So this is also 0, no force singularity. And this one is also 0 because of no charge singularity. There's no singularities in the Gaussian curvature. So if I had a spot here in the top where I had a charge singularity, a dislocation where I take where I pull out some atoms and I restructure my entire lattice, then I would get a non-zero D. If you're interested in seeing a really beautiful example like this, myself and Benny Davidovich have a paper, and very recent paper in PNAS, which deals exactly with how this sort of behavior can occur. But people have been doing this for decades. It's just more the
So why did you neglect it?
What?
When can you neglect it?
When there aren't any force, when there isn't any charge singularities. So when the curvature is smooth everywhere. Okay. If I had a dislocation here, it would be non-zero.
You're starting with a structure which is flat.
That's right. That's why I can.
Immediately becomes.
These are boundary conditions, right? I'm saying that because there's no singularity, I must choose this to be 0.
Okay.
It's setting. Right. I have 4 homogeneous solutions, and boundary conditions are exactly the ones that determine what their coefficients are. So the only guy I have left is BR squared plus my inhomogeneous term, and then BR squared will be set by boundary conditions. The last one. The last boundary condition is going to be that sigma RR on the boundary. I look at the boundary and I say, okay, what's the force, what's the normal force on the boundary? Why do I say normal force? Sigma RR is the force in the R direction pointing from the R direction, meaning it's the force outside. So typically, I'm going to have some boundary condition here. Usually what it is that sigma RR is equal to some number gamma. This gamma is just the surface tension. Okay, so think about the spherical cap. I take a substrate, I cut the spherical cap and I have a substrate. I put my 2D material, my graphene, and then because of van der Waals forces, it's actually being stretched a little bit on the boundary. So it's being forced to be flat by molecular forces that are typically what will happen, is molecular forces create adhesion to the sphere. But if I have a flat area here, there's also adhesion to this, and it kind of requires the system to stretch a little bit. If not, I put 0. Okay? But there's some kind of stretching force on the boundary. So this completely sets my boundary condition. I take this guy, I take a derivative to get sigma R. I don't want to go into the details. And that will tell me what this constant. Why? What is the important thing to get from it, from this whole story, is that now I know the stresses. Okay, the stresses are going to be sigma RR equals to this gamma from the boundary condition plus some other number that has to do with the boundary conditions. I don't care about that. Minus y alpha squared over 16 r squared. This is what I want you to take away. The stress, the radial stress in the entire material is non-zero and it's inhomogeneous. Okay? It's changing as a function of r just because I forced the system into the third dimension. So you cannot think of this system as being relaxed. What this means, for example, if you want to think of a concrete solid state ramification, is that if you do Raman scattering and look at the phonon frequencies here, here, they're going to shift. Okay? They shift by it's a fraction of a percent, but it does shift. Okay? That's telling you that the phonons, which are nothing but the excitations of the lattice, are being influenced by the fact that I forced the shape out of them. Okay.
So, raise your hand if you remember if the 2D or the G peak that should shift.
The what?
Which one? Hanan is asking which is the guy that which is the phonon that shifts.
If you do the Raman measurement, as we talked about it in the...
With EDR, right?
No,
Oh, not that one?
last class.
Oh, right,
Last
last one.
publication.
The phonon that shifts.
Which phonon will shift when you apply stress?
So if you guys remember, there's this E. There are two E phonons, an EU and an EG phonon. So two-dimensional phonons. One that's a symmetric change of the atoms, and one that's a dipolar change of the atoms. And the answer, which I think Hanan wanted, was it's the EG phonon that shifts directly due to the stress.
Yeah.
In
so
practice,
both of them.
because of the CIJKL, they both. It's known that they both
EJ
shift.
is the one.
It's known that they actually both shifting. Right?
Direction of propagation.
No, go back. The G is the optical phonon at K equals 0.
Yeah.
At the gamma point.
Yeah.
Take a look at the previous class.
Yeah.
Around essentially both will shift, but the
One will
G1
shift.
shifts.
One also splits, and the other one just shifts. So what we got is just from sticking it on a cap, that on one hand we have non-uniform strain. By the way, the strain, I can write it for you here. UR goes as this BR plus CR cubed. Okay, because the chi is r to the fourth, and u is derivatives, comes from derivatives, and so it turns out to be r cubed. But it's under tension everywhere. Okay, so this is something that experimentalists really always need to take into account. Good. Now let's do one more example. This is a very famous example called the Lamé solution. Lamé solution. Okay, and it's the following idea. Now we're talking flat. I take an annulus of 2D material. I make a hole inside, okay? And I put the inside and the out under different tensions. So I'm pulling outside and I'm pulling inside, keeping everything axisymmetric. I'm not breaking any symmetry, okay? So I have an R in and an R out. R out, we're going to assume that R out is much, much bigger than R in, so effectively infinite. So really it's like a huge sheet with a hole in the middle. Okay, and I have boundary conditions, which is I have some tension on the outside and also some tension on the inside. So if I were to ask you guys, what should happen? Just let's try to think about it, right? I take an annulus, I take just a 2D sheet, elastic material, a membrane, and now I stretch it a bit inside and I stretch it a bit outside. What's going to happen?
The band itself should grow. Right?
So presumably it will just stretch a bit, right? It will open, become a bit wider, the inside will become a little bit...
But that doesn't make sense.
Why not?
Well, because we established early, like in your last, when we stretch simply like a rectangle sheet, when we stretch it one way, it'll condense the other way.
Right?
This
I
way,
have a
there's
problem.
no place for it to
If
condense.
I stretch, I need to somehow react by condensing my material in the other way, but I can't do it. And that's what this is about. Think about it, right?
Yeah.
I want to somehow, if I'm going to buy myself material by stretching it, I have to pay for this material somehow, right? I have to somehow scrunch myself up. How am I going to do that? So something very strange is going to happen. And this is Lamé was the first person to show it. It turns out to be, it has nothing to do with an annulus. You can do it on a rectangle, but the solution on the rectangle is unknown. As you see, this is a difficult problem. Somehow doing it on an annulus makes it easy. Okay? So what we're going to do is first we're going to show that you're wrong. Okay? Because I'm going to just take this problem. Let's assume, make an answer that it stays flat. Okay? And I'll show you that there's a full solution. So there's no problem finding a solution to the flat problem. Here's the flat problem. I remind you the flat problem just means that grad 4 chi is 0, right? Because I kept it flat. And I have those four terms which we just did beforehand, A, B, C, D. There's no non-uniform solution. I can again toss all of the singular behaviors. Okay, it's a little bit more delicate to justify why you can toss all of the singular terms, but you can. Excuse me. And I end up with basically the same solution as before, without the non-uniform term. And I have sigma RR is equal to some, where am I? Some constant over R squared plus a different constant. And then when I apply boundary conditions, what I get is a fairly simple result. I have that it's equal to the tension on the outside plus the difference between the inside and the outside tension, the inner radius squared divided by R squared. So if you look at this, at the inner radius, I get exactly the inside tension. And then when I take R to infinity, I get the outside tension. Okay, very simple solution. Again, sigma RR, I didn't write it, but I can tell you what it is. It's 1 over R, d by dr of chi. Okay? Because I just take the derivatives of chi. However, I can also calculate sigma theta theta, which is just d by dr squared of chi, or if you want chi prime prime, is the hoop stress. The stress in the azimuthal direction as I look from the azimuthal direction. So this is the stress that's forcing my material to, it wants to either move apart tangentially or move closer tangentially. This is the guy that we just identified as problematic. And when I do the calculation, sigma theta theta is almost the same thing. TO. There's only one difference. Okay, why did this become a minus? Well, mathematically it's very simple. If I take a parabola, if I take something that's going to give me 1 over r squared, when I take one derivative divided by r, that's a log. But when I take two derivatives, I'm going to get a different sign. Okay? So now I have a minus sign. And what this means is that if the inner tension compared to the outer tension is strong enough, I have an area where this is negative. Right? I have an area where I'm stretching my material, but I have a negative hoop stress. My material wants to compress inside. That's not physical, right? How can I be stretching my material and it's compressing inside? So I have a solution, but it's thermodynamically unstable. And you can show that it's thermodynamically unstable. If you write the free energy of the material, then having negative hoop stress gives you a negative term in the free energy. This is like, we've already done Ginsburg-Landau in statistical mechanics, right? This is the same thing as having the quadratic term in the Ginsburg-Landau coefficient become negative. Oops, instability. Okay? So again, I show the solution, but what I get is that if Ti over Tio is larger than 2, then I have an area where sigma theta theta is less than 0, and that means basically that this entire region, R larger than Ri and smaller than some critical radius, which is equal to, again, I'm not going through the math, Ti over To minus 1. Just take this guy, put it equal to 0, and see in which radius it's less than 0. You get an annulus. So if I go back to my picture, what I found is that I have an unstable annulus to the flat solution. Okay? And if you look carefully, you'll see that as this ratio gets bigger and bigger, right, I can push this radius out further and further. I can make my unstable annulus bigger and bigger and bigger. How do I get over this? The answer is solution. Again, now we really won't go through the math. What we will assume is that Z is some function of R cosine M theta. So what I assume is that I create radial wrinkles in the system. I make an ansatz that there's some cosine, and I make the ansatz that M is very, very big and F is very, very small. This is what people call an asymptotically flat solution. So I go to the limit where I allow my system to bend, but I make the wrinkles very, very small so that on large enough scale I still look flat. But on a smaller scale, I can relieve the stress by adding material in these wrinkles. Okay? And then it turns out, I'm not going to go into the details, you can then do a scaling analysis of what M is going to relieve the stress. Basically what you need to say is that you want, maybe I'll just write, you want the sigma dot K. This tells you, this is kind of the force times the curvature. This is telling you how much force is being pushed outside by the wrinkles. How much outside force you're causing. And this is going to be like B times the fourth derivative of Z. This is the bending energy. So how much energy do I pay by bending my material? So you set one to the other, it gives you some scaling of M. The point is that what I'm doing is I'm relieving this stress. I create an area where sigma theta theta is actually exactly 0, or asymptotically 0. So I find a solution where instead of smaller than 0, everywhere it should be smaller than 0, I just put sigma theta theta equals 0. And the way I make the hoop stress 0 is by creating these wrinkles. And this is exactly what I started by showing you, if you remember last class. Okay? This is actually a paper where this problem is solved. Look at the number M. It's very big. Okay? So this is a controlled experiment for the Lamé solution. What they do here actually is they put this membrane on a water droplet, I think, because the water droplet creates a constant tension everywhere, not just on the boundaries. And then they get a very clean way to solve it. If you look carefully, you can also see that this M is just an approximation, because really it's not a pure cosine, right? You have superstructure. It's fractal, there's fractal behavior. Yes?
A couple of questions. First, theoretically, if you start doing this spool gradually in an ideal world, you cannot break symmetry.
You can.
So,
I just showed you. It's a spontaneous symmetry.
How it will choose?
How does it choose the wrinkle number?
Like physically, in a real system, there's no real symmetry, so it's okay. How does it choose? Like theoretically, if you start pulling, how do you choose which wrinkle number?
I said the selection of the wrinkle number is basically done by taking the term which you let me see if I can explain what the way this. So maybe I know what I want to say. Let me go back to here. How do we solve any problem where we have an instability? Okay, it's always works the following way. You make a simplified model which has a term which you can neglect. Okay, you neglect the term and you get a stable and unstable solution. the unstable solution is, sorry, you get an unstable solution. Then you fix the unstable solution, and what sets the new energy scale is the term that you neglected. So you have to pay a little bit of bending energy by creating these wrinkles. And basically the idea is that it's like a Ginzburg-Landau instability. You have an unstable solution, it's an unstable mode, and the mode will grow until the bending energy precisely compensates for the stretching energy. So you have a nonlinear effect. Similar to like in the nonlinear Schrödinger equation, say in Ginzburg-Landau you have a negative term, you go to the phase transition, you get an unstable mode that your superconductivity grows exponentially until delta cubed equals delta. So this is like your delta cube, the bending energy. It's like your delta cube. Does that make sense?
Mm-hmm.
So I really think these two examples, which of course, involve decades and maybe hundreds of years of work, kind of exemplify what geometry and nonlinearity do to two-dimensional systems. Okay, and why completely unrelated to quantum physics, to graphene, to transition metal dichalcogenes, any type of experiment which is done in 2D sheets, you always need to have in the back of your mind elasticity. I also want to use it as a kind of motivation for those of you who are interested in quantum physics to remember that soft physics is extremely important, and one of the least known fields and also one of the biggest research topics, and incidentally one which I work in a lot, is how elasticity and quantum mechanics kind of keep interplay to one another. This is a very useful, it's a very important field because it has to do with basically engineering devices. Engineering devices typically means doing something with strength. Okay, so now I want to go to the kind of qualitative part of today's talk. And let's go back to slide number 1, right? We are going back to put in a lattice now. We have strain, we have stress, we have this non-linearity. But now let's remember what it means. I remind you that di sigma ij was Hooke's law, right? F equals kx. So in equilibrium, F equals kx, F equals 0. But in non-equilibrium, of course, there should be some equation of motion, and this equation of motion is very simple. It's just the second time derivative of u. Why? Because what are u? U are the deformations of my atoms, or in other words, these are just the lattice excitations, right? These are just my phonons. So what this means, okay, is that strain in a system is actually excitation of phonons. And that means that if I take a quantum material, a material where electronics are important, and I put in strain, what I'm actually doing is starting to manipulate the electron-phonon interaction. Because as I put in the strain, I force my atoms to move. As I force my atoms to move, at some frequency, I am also moving around the electrons in the system. So the first kind of question that we should ask ourselves, maybe one more line. So how would I solve this problem? Again, it's very simple. Okay, this is textbook physics. You find it in Kittel. Just assume that your deformation is a plane wave. It's going to have some polarization. And so you take the second time derivative, omega squared u is equal to this horrible ci blah 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 di epsilon kl, right? The only thing to remember is that I have a derivative here, and I have a derivative in the strain, because strain is a derivative, right? So I get q squared. So omega squared goes as q squared. What does that mean? Omega goes like q. Those are acoustic phonons. So the strain in the system is the acoustic phonons of my lattice. Okay? When I say strain, I mean acoustic phonons. Optical phonons are different. So let's ask ourselves, what are the main mechanisms for electron-phonon interaction in a 2D lattice? Actually, almost to the end of the talk, everything I'm saying today is basically the same in 2 and 3 dimensions. Okay? And in fact, I'm going to show you examples in 2 and 3 dimensions so that we can compare them. So, okay, here's our favorite 2-dimensional lattice. I have a bunch of atoms, right? They're organized. And now I want to create a deformation. This is a deformation, this is a phonon, and its strain. You can see that dxu is non-zero, right? And there has to be something non-uniform for the strain to be non-zero, because the strain goes as a derivative. If I just create a uniform deformation, that's just shifting the entire lattice. That doesn't mean anything. Okay? What is this going to do? What happens when I do this?
Does the uniform shift everywhere?
No, I created a non-uniform shift. Right? This is a phonon, it has some wavelength, and it has a direction of propagation. Maybe this thing is a pulse moving through the system. But freezing time, what is this going to do to my system?
I guess it's going to attract more electrons to the center.
I'm going to remember that my atoms are ions, right? They have charge. If I bring them closer, I'm creating more positive charge. Where they're farther away, I'm creating less positive charge. So by creating a strain in the system, I'm also creating an electrostatic potential. And of course, what this means is that there's going to be a Coulomb interaction between my electrons which are flowing around through the system, say n of r, some electronic Coulomb potential. It's actually going to be screened. Did you talk about screened potentials? So u of r minus r prime should in principle be long range, like 1 over r. But it won't actually be because they'll be screening. And the charge that I've created from the phonon. Why do I say the charge? Because I create a deformation and I create what do we call bound charge, right? I create the charge that's not external, but it's just from the fact that I've pushed my atoms together. Why do I insist that this is the bound charge? Because it has to go as the divergence of u. Okay? And what this means is that this type of thing comes from longitudinal phonons. Phonons where the divergence of the phonon is non-zero. Okay, so this is one pretty standard type of electron-phonon interaction. The second big one is purely quantum mechanical in some sense. Okay, this is an interaction effect, right? This is coming from forces between charges. But there's something else that happens. What happens is that as I deform my system, I'm pushing my atoms closer and farther away. Now we should remember that, as you've done in the tight binding classes that you had with Hanan and with Yonatan, we should remember that every one of these atoms has electrons with some wave function. I push my atoms far apart, the overlap between the wave functions changes. And that means that the possible hopping, which goes as the integral of the overlap between the wave functions, is also changing. So strain changes my effective hopping. It basically means that the change in the effective hopping will go like the original hopping times how much I pushed. Okay, and you can actually show that the prefactor is pretty big. Yes?
Shouldn't it be a change by a phase also?
There will also often be a change in the phase. I'm just taking this all into account here. The point is that you have an effective change in the hopping as a result of the strain. What?
So epsilon is a complex?
Not epsilon. Epsilon is just the strain, but T can be complex. Yeah, delta T can be complex.
Okay. Delta
Let's think of it as an operator.
Yeah.
Okay. And so these will be the main ingredients. And what this tells us is that our electronic degrees of freedom and our strain are going to be strongly coupled. And this is useful because what it means is that we can use the strain to affect the electronics. Okay, and this is, $1 billion industry these days. So let's talk a little bit about quantum phase transitions. What are quantum phase transitions? Phase transitions which occur not as a result of temperature. I don't change temperature, but rather I stay at very low temperature, effectively zero temperature, and I change some parameter. And as I change some parameter, the system undergoes a phase transition. What drives phase transitions? So you've already done enough statistical mechanics to know that fluctuations drive phase transitions. What we learn in advanced stat mech is that you have the transition temperature, the Curie temperature, and at the temperature, thermal fluctuations diverge, right? But if I'm at zero temperature, I don't have thermal fluctuations. So what's driving the transition? The answer is it has to be quantum fluctuations, or in other words, it's Heisenberg's uncertainty principle. Because position, momentum, and are well defined, I have fluctuations that are occurring just due to the quantum mechanics, and somehow at the phase transition, these diverge. Okay? And one obvious thing that I can change at zero temperature is just the strain. So the strain is a classic tuning knob for driving through quantum phase transitions. It's maybe the most convenient knob for these things. So how do we describe this physically? So I happen to know that you've already done Ginsburg-Landau in statistical mechanics, which makes my life much easier, right? I'm just going to describe my system in 2 dimensions and an imaginary time. Imaginary time means instead of thinking of real time, I'm thinking of temperature. Okay, so energy space. And then I have some degree of freedom phi, which has a quartic term and a quadratic term and a quartic term. And when r changes sign, I undergo a second order phase transition. And this phi can be anything. It can be a vector. What vector is MJ? Magnetization. It can be a different vector, P. What is this guy? Ferroelectricity. Okay, it's the same as magnetization, but with an electric field. Does anybody know what Qij represents? What a typical second order tensor? Liquid crystal. That's right. This is a nematic phase transition. Okay, so electrons can undergo nematic phase transitions as well. I can have a scalar. The standard complex scalar is nothing but superconductivity in condensed matter. I don't have to have a scalar. I can have a vector complex. That's a vector superconductor. We won't talk about that today, but okay, it's a very interesting effect. Very common, very uncommon, but somehow in the recent years they seems to be popping up all over. And now, so I want to take my order parameter and I couple it to electrons. Okay? How do I couple it to electrons? Typically electrostatically. So usually my order parameter is something which also really has electrons in it, like a magnet. So there's a Coulomb interaction between it and the various other electrons in the system. So there's some Coulomb interaction. Or the other interaction, which we talked about before. And what I do now is I say, okay, let me take my electrons which are wandering around the system and do the theory trick of integrating them out. I account for the fluctuation, the Gaussian fluctuations, the quantum Gaussian fluctuations that occur because of the electron. That's precisely this Heisenberg uncertainty principle. And what that does is basically it adds additional terms. This should be phi, it's an error. It just adds additional terms to my Ginsburg-Landau. These terms are nothing but the electronic susceptibility. Okay, so usually what happens is that I get my quadratic term has a correction that should be phi squared, and chi is actually usually negative. Okay, so it pushes me towards the phase transition. But this is without strain. This is just having electrons in the system. Now I say let's also add strain, and I'm going to get the same thing. Because of electron-phonon coupling, I'm going to have a coupling between my strain and my electrons. And I'll have some kernel, which is, you know, what we talked about on the previous slide. Who cares what it is? I integrate out my electrons again, and now I start getting terms that involve the order parameter and the strain. And here is where I see how I can use the strain to control my phase transition. Because, for example, depending on symmetry, I might get linear coupling. What that means is that putting strain is like putting an electric field in the system, right? It forces a non-zero phi. So just putting strain, I can force phi to be non-zero. Or maybe because of symmetry A equals 0, but I have a non-zero term which is quadratic. What that means is that by choosing the sign and direction of the strain, I can basically modify my quadratic term. So I can push myself in and out of the phase transition. And this is kind of the holy grail of strain control of quantum materials. Can I engineer a system where I'll have a convenient function of the strain that will allow me to push in and out of the phase transition? And the answer is, of course, very often yes. I have, what, like 10 more minutes, something like that? Less? We started at 1:30, no?
Sorry, yeah.
So I have more than,
so
I have more than 10 minutes. I have 10 to 15 minutes. I'm even in good.
I tried to strain you.
That was compressive strain. It hurts.
Yeah.
Okay, I just want to show you now 3 examples of how you use strain to control the phase, and then we end. And here's the funny thing. Everything I told you now, I use pictures from 2 dimensions, right? And it's very clear that strain is kind of a 2-dimensional object. It's very strong in 2 dimensions. It should be perfect. It turns out that theoretically it's very easy to control materials using strain in 2 dimensions. So if I'm using a pen and paper, piece of cake. But as I'm going to show you in experiment, it turns out to be really difficult. And the reason is not so much the strain, but the fact that 2D experiments are very difficult. So let me show you.
Here.
In every one of these examples, what I'm going to do is I'm going to show you first a bulk material, a 3-dimensional system, which is quasi 2D, but it's actually a bulk crystal. And here you see the strain effect really nicely. And then I'll show you what happens in 2D. Okay? So what you see here is a very famous compound, uranium germanium-2. It's a famous unconventional superconductor that's also a ferromagnet at the same time. And what you see here is its Curie temperature where it becomes ferromagnetic as a function of pressure. I remind you that pressure is just a trace of the strain tensor. Epsilon xx plus epsilon yy plus epsilon zz. And you see really beautifully how you apply pressure and you just lower the temperature, so you're changing the quadratic term. Why is it that the quadratic term couples to the strain? The answer is symmetry. Magnetism breaks time reversal symmetry, okay? And strain does not break time reversal symmetry, so strain can only couple to m squared. So by definition, if I take an order parameter that has a different symmetry from strain, the strain will couple to it quadratically, which means it will control the phase diagram, which is exactly what you look. And also, surprise, surprise, it's very common. There is a dome of unconventional superconductivity very near the quantum critical point. Okay, this is a common and very interesting feature. As you go to the critical point, you increase the quantum fluctuations, and quantum fluctuations are also good for superconductivity, so you get superconductivity. What happens in 2D? So this is a very hot material these days, chromium samarium bromide. Okay, it's a 2D, very complicated material, a TMD, sort of. Right, it's not actually a TMD. Yeah, it looks a little bit like, but it's not. And what this experiment, what they do is they make a bilayer. Okay, it's one of a field of 2-dimensional magnets, which is a very hot topic these days, because in principle there are reasons why magnetism should not be 2-dimensional, but that it very much is. And they just put it on a piezoelectric substrate, and then they can strain it. So they strain the bilayer, and what you see here is kind of what happens. They strain the bilayer, and then they look at reflectivity, at Raman.
Can anyone guess why you can't have magnetism in 2D?
I know that you discussed it.
Yeah.
It's the stupidest theorem in physics. I mean, the most useless correct theorem in physics. So the Merman-Wagner theorem, which says that there's no long-range order in 2 dimensions, it is the most useless theorem in physics because it's always long-range order in 2 dimensions.
That was basically because of the phonon excitation.
That's right.
Yeah, so in this case,
Goldstone excitation.
Magnetic excitation.
So here is where I want to talk about a little bit 2 dimensions. It turns out the strain controls the phase beautifully here, but so they take a bilayer of the CR-SBR. It's known to be an in-plane ferromagnet. Okay, and then when you strain it, actually what happens is that one of the layers flips, and it becomes a layer antiferromagnet. How do they measure this? The answer is they look at the Raman spectra, so they measure reflectivity, and they see some sort of line shape. And the line shape is different when you have ferromagnetic and antiferromagnetic coupling. So if you look here on the right, you have a map here of the strain and of the energy, so the wavelength of the excitation. So they're looking at different phonon modes. Okay? And as you see, what you see is that you have these modes that are here, and then at some strain they go away. What this means is that the symmetry is changing, because a phonon that beforehand spoke to my electric field is suddenly not speaking to my electric field. That means that the symmetry changed. So this, when one type of phonon disappears and another doesn't, this tells me that I'm undergoing a phase transition. So what's happening here is they wanted to see how you go from a ferromagnet to a non-ferromagnet, but that's not what happens. Instead, the bilayer becomes an antiferromagnet. Okay, and this is one of the nasty parts about 2 dimensions. First of all, it's very hard to measure. I can't just measure magnetism. Why can't I just take this material and measure its magnetic field? It's a dumb answer. It's just one layer, one atomic layer. It's too small. Okay? I can't do it. So that means I have to do something, fancy. So then it becomes very fancy. And also, because of the Merman-Wagner theorem, the system hates being ordered. So it's always going to find ways to create nasty kinds of order that are complicated and a little bit less order than what I would like. Okay?
But sorry, this is like, sure, I agree that one explanation could be that it's changed from ferromagnetic to anti-ferromagnetic, but you could, you just showed us how you're changing the interaction with the phonons, or the phonons themselves when you're straining.
Yeah, so again, I didn't go into too many details, but this spectra is the bulk spectra. It has a well-defined ferromagnetic and anti-ferromagnetic phase, and they show very clearly that you just go from one spectrum to the other. So that's probably what it is. But yeah, it's really nasty. Okay? So, okay, that was one. So magnetism breaks time reversal symmetry. Now let's talk about a phase that breaks inversion symmetry, ferroelectricity. So the creation of spontaneous dipole moments in the system. And again, let's play this game. There's a very, very famous set of materials. They're called perovskites. They're what people use nowadays in all of your FRAM and all of your low-powered memory in your phones. Are basically all based on ferroelectric materials to create the switches. Okay, this is a material called strontium titanate. It is also a very famous quantum material. It is more or less the first unconventional superconductor to be found. It was discovered in 1960. So only 3 years after Bardeen, Cooper, and Schrieffer showed that BCS theorem requires superconductivity. The superconductivity requires a high density of electrons and a good metal. And then 3 years later, strontium titanate is actually a very bad, it's a semiconductor, it's an insulator unless you dope it, and it superconducts at a density of electrons that is so low that when you're looking at the number, when you look at the coherence length, meaning the typical distance between electrons, it is less than the physical distance between the electrons in the system. Okay, so the system somehow superconducts even when 2 electrons are a micron apart. Like you dump like 6 electrons in the system and they suddenly superconduct. It's a really crazy material. But for us, what's important is that the system also undergoes a ferroelectric transition. So this is very old data from the early 70s by the way, Burkhardt and by a guy called Müller, who was much better known for having discovered high temperature superconductivity. Before that, he was doing strontium titanate. And what you see here is that as I increase the stress, which is I just apply pressure, so I'm changing the strain in the system, at some point spontaneously I get a ferroelectric moment. Okay, you can ignore all these other lines which have some other interpretation. The point is that spontaneously I create non-zero polarization in the system. So this is a second order phase transition. Beautiful Landau theory typically works for it. So this is 3D. So strain controls the phase. Here is 2D. So ferroelectricity in 2 dimensions is also a very hot topic today because it's great for devices. Being able to create electric switches at low temperature.
Actually, we have Moshe speaking about this.
Great.
Next.
Oh, really? Oh, good. Okay. So that will. Here's a 30-second introduction.
Yeah,
to Moshe
you can use the teaser.
So it turns out that if you take just 2 standard, almost any 2-dimensional materials, and you stack 2 of them on one another, as long as they have some kind of non-trivial lattice structure, this specifically is, I believe, tungsten ditelleride. You see that each of the layers sort of has a weird shape. So when I put one on another, it turns out that by sliding like this back and forth, I break inversion. So up and down change meaning as I slide back and forth. So this material becomes a ferroelectric where it creates an out-of-plane electric field as I slide like this. Okay? So what basically happens is that there are 2 stable configurations, and then in the middle there's an unstable configuration, which is symmetric and doesn't have an electric field. Again, it's a Ginzburg-Landau theory. And what you can see here, it's really difficult to measure. So you have to create some substrate, you put the tungsten ditelleride bilayer, then you take an AFM tip, which has some kind of polarized material on top, and you very, very carefully measure the local electric field, and what you see is that indeed you will get hysteresis, okay? So I haven't even showed you how you can control this system with stress. but it's pretty obvious if you think about it that sliding these two materials is nothing but applying a strain, right? I'm creating a deformation. So it turns out that this kind of energy landscape is the stress one. And why didn't I show you an experiment? Can anybody guess?
No one.
Hasn't been done, okay? Nobody succeeded yet. And it's just very hard. Okay. Actually doing a controlled strain experiment where you measure the polar moment as a function of strain on a bilayer is like insane, right?
Okay.
You would have to work really, really hard. And
I mean, the problem is measuring the moment, not the
yeah. No, I mean, also if you want to do a continuous sliding, I think it's very difficult because it will just lock to.
Yeah.
And there are so many different configurations that I would prefer to lock to.
Yeah.
And so you probably need to somehow apply an in-plane field. Anyway, it hasn't been, as far as I know, it hasn't been done. And I happen to be quite interested in this field, so I hope I would know if someone did. If anybody sees a brand new Nature paper on doing that, let me know. Okay, last example. Again, a three-dimensional system which is quasi-2D. This is called iron selenide. It's one of the most famous iron-based superconductors. It basically is created, it's these quasi-2D layers of iron and selenium. And one of the things that's known about it is that it spontaneously undergoes a nematic phase transition. So somehow the electrons in the system spontaneously form quadrupole moments. The way you see it is you look at the Fermi surface, so you look at the electronic structure, and as you can see, it creates these peanut shapes below some transition temperature. So basically, circular Fermi surfaces become like ellipses, and they just spontaneously pick a direction. The reason why you see two different directions here is because the material has different domains, so it averages. When you do the experiment, you see some domains like this and some domains like that. But the other thing that's very nice about this material, so it has a nematic phase where it creates this quadrupole odor. As you see again, you can control this by some parameter. It's actually usually sulfur doping. And as you go to the critical point, you get a superconducting dome. The sulfur doping is actually just applying chemical pressure in the system. So you push in some atoms that don't fit, you force the system to strain a bit. But what I really want to show you is this three-dimensional phase diagram where on one axis they change the doping, they add some sulfur, and on the other one they apply pressure. And each one of these is like a phase diagram. So you see that as you apply pressure, this nematic area becomes narrower and narrower and narrower. You can control how much of the area is nematic, and you also see that superconductivity just jumps up. So as you kill the nematic order with the pressure, you enhance the fluctuations and you create additional superconductivity. Okay? So again, beautiful example of how a nematic order is controlled somehow by strain and also superconductivity. The same thing happens in 2 dimensions, except again, it's much harder to see. So what is this?
Twisted bilayer graphene?
No, this is twisted bilayer graphene. Okay? This is a famous experiment from a few years ago. You take bilayer graphene, you stack and twist 2 sets of bilayer graphene on one another, and you look at you do STM to look at the electronic behavior. And as a function of twist, look what happens. Here it really looks like a Moiré pattern, right? You just see the 6-fold symmetry, and then somehow at some point you begin to form stripes. So you've broken the rotational 3-fold symmetry down to 2-fold symmetry. This is precisely a nematic phase transition, and it is of course occurring because of strain. As I push my system towards a specific angle, I apply these strains which make the system want to spontaneously form nematic order. Okay? So this kind of summarizes what I wanted to show you.
Sorry. Why do you say strain, not just like the superlattice?
Yeah, superlattice equals strain, as I just showed you. It's an acoustic form.
No, sure, but I'm saying you can also have a superlattice without acoustic strain.
No. A superlattice is strain. That's what it means. It's just a fancy way of saying.
You can just look at how the coupling is changing from the bottom sides to the top sides.
Yes.
Independently from.
Yes. What changes the Hawking?
Hmm?
What is changing the Hawking? What's actually changing the Hawking?
I mean,
the wave function overlap, right? So it's a strain
Okay,
effect.
if you want to call it strain.
But it's, this is the part that I'm trying to stress, right? That behind everything is the strain field, okay? And also, I believe that specifically for this case, it also turns out to be that it's a strain effect.
I think so, but
It's in this case, it's just by symmetry you can show that it has to be strain.
I'm just saying it
Yeah,
might
yeah.
be a bit confusing if you're referring
So-
to everything as strain.
So the nice thing about nematicity is that it's automatically strained, and the reason is that the nematic quadrupole moment has the same symmetry as the strain tensor. So if Qij is non-zero, by definition epsilon ij is non-zero. Okay? So that's why it's very easy for me. Whenever I see nematic, I can say it's a strain effect, and I'm done. And that's what I meant. Okay? All right. So that ends today. I hope I managed to show you. Okay, except for all these citations, whatever. That strain is something which is actually completely universal. It has to do with geometry rather than a specific lattice structure. But on the other hand, the moment I include quantum mechanics, or if you want, the moment I include electrons, it becomes a really powerful tool, not just in 3 dimensions, but actually especially in 2 dimensions where it might be very hard to measure, but also the only thing that I can control practically is how much I strain my system. Okie dokie. Any questions or additional questions? I will send the notes with all these strain calculations and this PowerPoint presentation to Hannah. So,
I'll send it to you. Bobby.
Now we're back downstairs, or here?
No. Today,
this is just a make
tomorrow,
class.
yes. Tomorrow.
What room are we in tomorrow?
Sorry, no. Tomorrow we're here as well.
Also here, okay.
Yeah, there's. Wait,
Tomorrow's the normal day.
I'm confused. I have to. No, because they. Let me double check. I'll put a message on.
Yeah, please do.
Actually, it was scheduled up to 3.
Sorry.
Class was till 3.